Have you ever wondered why different instruments, such as a guitar, a cello, or a piano, sound different even if they're playing the exact same note? In order to understand the unique sound of an instrument, usually called timbre, we need to learn a little bit about the physics of waves on a string. I'm Dr. Jarusik. I teach physics and astronomy here at UCF, and music has always been a treasured hobby of mine. I primarily play piano and guitar, but I've recently been fiddling around with a cello and a violin. A word of warning, I'm a complete novice at these instruments, so please don't think I'm pretending to know how to actually play them. Okay, let's jump right in. The frequency or pitch of a sound wave produced by a vibrating string depends on three quantities: the length of the string, the mass of the string, and the string tension. If the wavelength is equal to the string length, which is not always the case, then the relationship looks like this. So if you decrease the string length by pushing down somewhere with your finger, the frequency or pitch goes up. If I loosen the string, reducing the string tension, the pitch goes down. If I play a heavier cello string with roughly the same length and tension as a lighter string, I can expect to hear a lower pitch. Okay, let's move on to wave propagation and reflection. I'll use this long spring to demonstrate our guitar or cello string. When I produce an up and down pulse on the spring, it propagates to the right, but once it reaches a fixed boundary, such as the bridge of the guitar or maybe the point where my finger is pushing down on the string, the pulse reflects back upside down. This is the key to understanding standing waves. Sorry, I didn't stutter. Standing waves are waves that appear to not propagate, but they're composed from waves that do propagate. Weird. You see, waves that are right on top of each other add together point by point. If the two waves are both up at a point, then they add together constructively. If at some other point along the string one wave is up while the other is down, the two amplitudes, or loudness, subtract. They can even cancel out completely. Standing wave consists of the rightward traveling wave plus the upside down, reflected, leftward traveling wave. Since the two waves are traveling at the same speed, they have to, they're on the same string, there are points where the string doesn't move at all. We call them nodes. And places where the string moves up and down a lot, well, we call them antinodes. And this is a standing wave. Let's look at some examples. The easiest way for the string to vibrate is at its fundamental frequency, or first harmonic, which looks like an up and down only version of skipping rope. Remember that we can think of this string motion as being composed of rightward and leftward traveling waves that either add or subtract point by point. If I shake the string a little faster, I can get the first overtone, or second harmonic, which has a node right in the middle. Shake a little faster and add a little more energy, and I can get the second overtone, or third harmonic. And you can clearly see two nodes. Now I'm really having a hard time. I'm shaking this spring string as fast as I can, adding a lot of energy, and I've got the fourth harmonic with 3 nodes. By the way, I can force the guitar string to vibrate in any of these harmonics just by gently placing my finger on the string right where one of those nodes should be. Finally, we're ready to answer our initial question. Why do instruments have different timbres? AKA, why do they sound differently? When you play an instrument, the strings actually vibrate in all of the different modes of vibration, all at the same time. The fundamental frequency is the note we want to hear. It has usually the biggest amplitude, unless you're still learning like me. Anyway, the other harmonics are there too, all added together at different volumes. And it's this harmonic content that makes an instrument sound the way it does. Of course, the higher the frequency, the more energy it takes to excite that mode. You can really see me struggling with that fourth mode, for example. So the larger the number of the harmonic, the quieter that mode is. All of this applies to every instrument. I just chose to use stringed instruments because they're a little easier to understand. So that's why a particular instrument has a unique sound. And if you're learning a new instrument like me, don't get upset if it doesn't always sound the way you wanted it to. You just made the harmonic content a little more interesting.